So we have seen different kinds of signals, their properties, and how to model them, how to analyze them, what happens when you shift in time, scaling, everything. So now we have a short summary of everything that we saw about signals. So if you can understand or if you can recollect whatever we studied so far from these 3 slides, then it means that you have a good understanding of signals. So this is a good summary of everything that we have seen so far. Okay, so what have we seen? So we first saw what are continuous time signals, and then we saw some examples, standard examples of them, which are the step function, the Dirac delta function, and the rectangular function, the sinusoid, the real valued sinusoid, and the complex valued sinusoid. These are the key functions which we'll repeatedly keep using again and again in future. Okay, we saw that we stick to continuous time signal, which means the time and amplitude are from a continuum, and negative time is basically referring to the time duration before the circuit was initialized. So if you start the circuit's source, let's say which is a battery or an AC source at a particular time instant, then we'll call that as the origin. Basically that is t equal to 0. The origin of the signal is modeled by t equal to 0, and anything that happened in the circuit before turning on the circuit is what we refer to as the negative time. Okay, so that is basically a mathematical model. And for continuous time signals, we'll say that the signal actually exists from minus infinity to plus infinity. This is purely a mathematical model. Of course, in real life, signals exist only from a of course, in real life, signals exist only in a finite period of time, which means if I say that a signal exists from, let's say, time t0 to t1, so of course in real life the signal exists only for a finite duration. For example, if I say that a signal starts at time t0, of course in real life a signal has only a finite duration, which means it starts at some particular time and it ends at some particular time. So let's say a signal starts at time t0 and ends after some time duration which is equal to t1 seconds. So if we want to actually capture this real life signal, what do? We say that okay, we'll have a window which is of this duration, okay, and that is modeled by this rectangular function. Basically we shifted this rectangular function and scaled it to model this window, and you can multiply your infinitely long mathematical signal. So when I say a cos omega t signal is what that we have as the source, of course the source cannot exist from minus infinity to plus infinity in real life, right? So it exists only from some time duration till some time duration. Let us say it existed from t0 to t0 plus t1. Then the real life signal is basically nothing but a product of this window with your actual mathematical signal. So when you multiply these two, what do you get? You get something which is non-zero only in this window and zero everywhere else, right? So this is what we refer to as windowing of signals. So if you want to capture real world signals analytically, then basically what you would do is multiply your signal with a window function. So this is one way of modeling real world signals. But what we will do is, in most of our analysis, we will say our window is really long, that we can think of the entire signal to exist from minus infinity to plus infinity. Once again, we are all going to make approximations so that it makes our life simple. So analysis becomes simpler when you assume the window is really long and your observation is from minus infinity to plus infinity. Otherwise, you will have to take into account this t0 and t0 plus 1. There is a multiplication of this rectangular function everywhere, which is a little tedious. So we will get rid of this window function by approximating that our signal exists from minus infinity to plus infinity. And then of course we know how to shift our signal, how to scale our signal, what is the effect of shifting where it moves to the left or right, or the effect of scaling where the signal gets stretched or compressed. Okay. And then when we have to do both the operations simultaneously, we saw that there are two ways possible. Either you shift first and scale, or you scale first and then shift. we saw the effects of what happens when you do one of these operations. Okay, and then we saw phasors, which are very important functions which we'll keep using repeatedly. Phasors are nothing but eigenfunctions of the integration differentiation operator. Remember, in an electronic circuit, most often you will have either a resistor or a capacitor or an inductor. So these are the three components which we use repeatedly again to construct big electronic circuits. So anything can be eventually modeled as one of these components or a combination of these components. So in order to study these electronic circuits, we need to know how signals are affected by these components. So an inductor could be modeled using an integrator, and a capacitor could be modeled using a differentiator. That's what we saw earlier, right? So we need to see how these components affect our signals. So in order to understand that, we use the eigenfunction of this integration differentiation operation. So that helped us to simplify our analysis, and the eigenfunction simply turned out to be a phasor, which is a complex sinusoid. So this choice of signal helps us to easily compute whatever that is going on inside a capacitor or an inductor. Otherwise, the analysis becomes too difficult. You have to solve a lot of differential equations. But those differential equations are simplified when we use phasors, and the analysis becomes much simpler. And we saw that phasors introduce a new notion of frequency, and that is known as negative frequency. The concept of negative frequency does not really make sense for real valued signals, but it makes sense for phasors, complex valued signals, because for phasors we have a direction of rotation, and when the direction of rotation is clockwise, we say that the frequency with which it is rotating is negative. Okay, and then the moment we have complex valued signals, we need to visualize them, and that requires two different plots. We saw that what they are, and we saw different kinds of symmetries when we visualize signals. So we saw that there is even odd symmetry or conjugate symmetry or skew symmetry. And then we saw other properties of signals such as periodicity, and once a periodic signal is given to you, from its period you can find out what is its angular frequency or its linear frequency. Okay, and then we saw what is the energy of a signal, and the energy of the signal is essentially equivalent to the length of a signal when you think of the signal as a vector. Okay, so you say that the energy is equivalent to squared length of the vector. Okay, and it helps us later to compare multiple signals. So if I was given a signal x of t and I want to say that the x of t signal is approximately equal to the signal y of t, then we can say that by claiming that the difference of these two signals have an energy which is almost equal to 0. So if this is true, so the energy of x minus y is 0, then we can say that the signal's x of yt is approximately the same as the signal y of t. So this is one scenario where the notion of energy becomes very helpful for us. We'll see this being used later. Okay. So similarly, the power of the signal is essentially nothing but the energy, but averaged over some time, and this time you will take it to infinity, and hence we say that the asymptotic time average of energy is the power. And we also saw that all periodic signals are power signals. They have infinite energy. Okay, because of this reason, all practical signals are energy signals, because we saw that they are finite duration, hence they are also aperiodic and they are energy signals. But of course, what we'll do in theory is the window function is extended to infinity, which makes it approximately periodic, or we'll assume that they are periodic, and it helps in analysis. And in this course, we also saw what are orthogonal signals, right? So whenever the component of one signal along the other signal is 0, then we say that they are orthogonal signals. In other words, in the notion of vectors, they are perpendicular to one another. So they can be either real valued signal or they can be complex valued signal. We saw that the even component is orthogonal to the odd component, and we also saw that when you add orthogonal signals, the energies add up and the powers also add up. Now this is a very nice summary of what happens to signals and their properties when you do some kind of manipulation on top of them. So if you add two signals, what happens to their properties? When you multiply two signals, what happens to their properties? When you shift them in time, what happens to its property? When you scale in time, what happens to its property? So we saw what happens for the symmetry case with individual tables, right? So you can check what happens to the symmetry case. It depends upon what happens to the individual signals symmetry and when they're added up in their product. So there is a table for each of these cells here. Of course, when you shift in time, the symmetry changes. So we have that here. When you scale in time, remember all symmetries are about the origin, which means the symmetries do not change because scaling is also about the origin. And periodicity, we saw that when you add or multiply, the periodicity remains only if the individual periods combine together to have a rational ratio. And if you shift, of course, they are still periodic. If you scale in time, it stretches or expands, which means the period also stretches or expands. Similarly for energy and the power, we said because of the averaging operation, it remains the same. And time shifting really does not affect any of these things. So these are the notions that we saw earlier, how each of the properties get affected by their manipulation individually. So this is a good summary in the tabular form.